When doctors or scientists want to peer into living tissue, there's always a trade-off between how deep they can probe and how clear a picture they can get. With light microscopes, researchers can see submicron-resolution structures inside cells or tissue, but only as deep as the millimeter or so that light can penetrate without scattering. Magnetic resonance imaging, MRI, uses radio frequencies that can reach everywhere in the body, but the technique provides low resolution, about a millimeter, or 1,000 times worse than light. A University of California, Berkeley, researcher has now shown that microscopic diamond tracers can provide information via MRI and optical fluorescence simultaneously, potentially allowing scientists to get high-quality images up to a centimeter below the surface of tissue, 10 times deeper than L. By using two modes of observation, the technique also could allow faster imaging. The technique would be useful primarily for studying cells and tissue outside the body, probing blood or other fluids for chemical markers of disease, or for physiological studies in animals. This is perhaps the first demonstration that the same object can be imaged in optics and hyperpolarized MRI simultaneously, said Ashok Ajoy, UC Berkeley Assistant Professor of Chemistry. There is a lot of information you can get in combination, because the two modes are better than the sum of their parts. This opens up many possibilities, where you can accelerate the imaging of these diamond tracers in a medium by several orders of magnitude. The technique, which Ajoy and his colleagues report this week in the journal Proceedings of the National Academy of Sciences, utilizes a relatively new type. Ajoy exploits an isotope of carbon, carbon-13, C13, that occurs naturally in the diamond particles at about 1% concentration, but also could be enriched further by replacing many of the dominant carbon atoms, carbon-12. Carbon-13 nuclei are more readily aligned, or polarized, by nearby spin-polarized vacancy centers, which become polarized at the same time they fluoresce after being illuminated with a laser. The polarized C13 nuclei yield a stronger signal for nuclear magnetic resonance, NMR, the technique at the heart of MRI. As a result, these hyperpolarized diamonds can be detected both optically, because of the fluorescent nitrogen vacancy centers, and at radio frequencies, because of the spin-polarized carbon-13. This allows simultaneous imaging by two of the best techniques available, with particular benefit when looking deep inside tissues that scatter visible light. Optical imaging suffers greatly when you go in deep tissue. Even beyond 1 mm, you get a lot of optical scattering. This is a major problem, Ajoy said. The advantage here is that the imaging can be done in radio frequencies and optical light using the same diamond tracer. The same version of MRI that you use for imaging inside people can be used for imaging these diamond particles, even when the optical fluorescence signature is completely scattered out. Detecting nuclear spin. Ajoy focuses on improving NMR, a very precise way of identifying molecules, and its. Thanks for watching. Please subscribe my channel for more updates.